Hello, everyone. It's local time, 13 o'clock on 17th November. So this session is the desalination membrane preparation and characteristics. And we have 4 speakers in this session. The first speaker is from Prof. Liu Zhuang from Sichuan University of China. His topic is on ion responsive membranes and ion separation membranes. During his talk, if you have questions, please type your questions in the chat box. Okay, without further ado, let's welcome Prof. Liu Zhuang for his talk.
Okay, thank you for the shipping's introduction. Good afternoon, ladies and gentlemen. It's my honor to give this presentation on ion responsive membranes and ion separation membranes. My name is Zhuang Liu from Sichuan University of China. So as we know, the metal ions plays very important roles in life, environmental and energies such as bacteria. So my presentation include 2 parts. One is ion responsive membranes. The other is ion separation membranes. So as we know, the potassium ions is the most abundant intercellular metal ions and plays an important role in the biological systems for managing the extracellular oxide with sodium ions. So as we know, the intercellular potassium concentration is about 30 times higher as that outside the cell. So, however, the disorder of potassium concentration between the intracellular and the extracellular fluid is always associated with certain disease and cause the abnormal increase of the extracellular potassium concentration. So the increase of the potassium concentration is a commendable signal for drug control release. So membranes are expected with potassium responsive permeability. On the other hand, the lead ions can cause damage to the certain nervous systems and the dysfunctional of the kidneys of the human beings. So particular to the children with harmful effect on the electro development. So the heavy metal ions leader can actually in the human body through the water intake and the food chains. It's the famous flowing water pollution even in China, in USA. So because the drinking water in America has been found with lead ions with high concentrations than the safety stance. So the discharge stance of the leader is very lead, which is a trace lift of 100 ppm, and so select detection and remove such trace lead ions is very important. And here we designed 2 kind of ions responsive membranes. One is positivity potassium responsive gating membranes. The membrane pores opens by recognizing the presence rather than absence of potassium ions in the environment. So the membranes are fabricated by 2 steps. The first, the plasma graft polymerization, and then the chemical modification. So when the potassium ions appeared in the environment, it can be recognized and captured by the conducer and form the sandwich-like complex. As a result, the graft compolymer shrink and the membrane pores opened. When the potassium ions is removed from the crown ether, the graft copolymer changes square and close the membrane pores. However, the other ions such as sodium or calcium or magnesium can't target such responsive gating behavior of the membrane. So first, the SEM image shows that the compolymers can be grafted onto both the outer surface and the inner surface of the membrane pores by using the two-stepped method. So the more copolymer are grafted, the smaller of the pore size. So the result shows that the potassium response switch in factor of the copolymer graft membranes with different graft yield or graft rate. So with increase the graft rate, the more the graft polymer here, the solution flux reduced in both pure water and potassium solution. So when the graft yield is about 4.77 and 2.27, so the potassium target graft rate is the largest in the study. So it's about 54. So this shows that when the pure water is used, the graft copolymer is swell and the membrane pore is closed, so the flux is very lower. So when the solution is changed from pure water to the ion solutions, only potassium ions can open the membranes. So while the others ions can, the flux of the ion other ion solutions is very small. So it's a very slight differences of the polymer in pure water and the other ions is the result of salt or out effect of the target of the graft copolymer. So the effect of the pore size of the graft membrane can be calculated using Hagen-Poiseuille equation. So at the in the water solution, the pore size is about 43 nanometer. When in the potassium ions, it about twice increased. So also the potassium responsive gating function of the membranes are rapid and reversible. When the environmental solution is changed from the pure water to potassium ions, the solution flux increased within 1 minute. The responsive time is very short. When the membrane is washed with pure water, it is also the flux decreased rapid within 50 seconds is very quick. So moreover, the surface of the membranes transfer from hydrophilic to hydrophobic by the introduced by the potassium ions. So only in the potassium ions, the surface of the membrane become hydrophobic. So that shows that the pore size, and we find that the diffusional permeability character of such positivity potassium responsive membranes is caused by the changing the pore size and the surface width. So for the hydrophobic molecular, only the small molecular size can permit it to diffuse across the membrane upon in the potassium solutions. While for the larger molecular size, it is retested to diffusion through the membranes within the potassium ions. So the other work is second, we designed a negative leader ions responsive gating membrane, which is quite different from the absorbed one, the potassium responsive membranes. Resin recognized the leader ions in the environmental, the membranes pores are closed. So the crown is here is different from the potassium responsive ones. So the 18 crown 6 units act as the host molecules, which can select recognize the leader ions to form the one by one host ghost complex. So the crown user can capture the trace leader ions and forms the charged complex groups. So the polymer can change from a shrinking state to the swirling states in response to the trace ions. As a result, the flux will decrease adversely, which can strongly to prove the presence of trace leader ions in the environment. So when the complexation reaches saturation states, so we just increase the temperature, so the leader ions can release from the compolymers and the membranes can use it again. So first, we in this figure we shows the temperature depends of the solution flux through the gating membrane. So the membrane can responsive to the trace lever of the leader ions. So the value of the gating compatibility reaches the smallest at this concentration or this temperature, which can consider as the operating temperature to detection the leader ions. So we just tested the effect of this membrane. So the gating membrane can use to detect the leader ions by the flux decreased. So when we change the pure water to the ions solutions with leader ions, so the flux of the membrane and decreased significantly. So the pore size of the membrane can calculate it as decreased too. So on the other hand, the gating membrane also can use to remove the trace leader ions, as the remove rate of the membranes can reach the about 78%. So even for the result confirms that the gating membrane graft of enough copolymer can effectively and selectively to remove the trace leader ions from the solution environmental, even through the other ions such as potassium or Ba ions here. So in this part, the conclusion is the potassium responsive membranes brings new novel materials for chemical and biomedical separations, tissue engineering, and sensors that can be responsive to potassium ions have been developed. And second, the leader responsive gating membranes are promising for online detection of trace leader ions on wastewater discharge and timely treatment of the heavy metal leader ions wastewater. So secondly, the ion responsive membranes, for the reason the membranes with two-dimensional or nano channels are developed for application of ion separation because of the unifast transport through the two-dimensional nano channels. But such as using the graphene oxide membranes. So, however, the problem is the normal graphene oxide membranes is quite unstable in water. So the geomembranes is breaking when putting the membrane in the water. So building the interline crosslinker by the ions or the molecule will, that is because it is because the geoshells, it contains a lot of oxide groups. It can form the strongly hydrogen bonding of with water molecule to form the respective hydrogen forms to make the solution to make the membrane unstable in water. So using the to building the interlayer crosslinker using ions or molecular will make the membranes stable in the water. However, the ion crosslinker will also unstable in acid or base solution. So the polymer crosslinkers is considered as to distribute of well diffusion of the nanochannels. That is, if we use the organic molecule to cross-link the geomembranes, the size of the nanochannel will increase. So that is not careful for ion separation. So here we just in this work our substrate is to reduce the oxide groups on the geo nanosheets. So in the geomembranes, so the particle reduce the graphene oxide sheets are prepared reducing the oxide groups on the membranes. So by vacuum filtration of the on the membrane filters, the the geomembranes the new geomembranes are forms are prepared. So due to the slight reduce of the oxidized groups, the interline of the membrane size short. So as a result, both weaken the reflects the hydration force and the pi and increase the pi exchange between the geomembranes contribute to the high stable of the geomembrane in the aqueous solution. So the first is that importantly the prepared the PL geo nanosheets is have the carbon and the oxide rate is about 4.2. So the membranes also has the layered nanostructure. So the membranes are very the interspace of the membranes are decreased, and the membrane, as our research shows, that is very stable in water. That one is not stable in water, but our membrane is very stable in water and the acid solution and the base solution. And so differently, we just use the different membrane substrate to prepare the membrane. Our membrane is very stable in water. So that's the first part of the work. The second is the result shows that we reduce the oxide groups at a high temperature. The nano channel is ununiform. So here, this work, we just reduce the oxide groups of the geomembranes at the room temperature, so it can forms the uniform nanochannels. So we just use the full width at the half of the max XRD result to show the uniform property of the membrane. So here shows that the FWHF value of the geomembrane is very small. That means the nanochannel is uniform. So our new membrane is just a little increased, but the proposed work is very large. So the result shows that our membrane have a very large separation factor for potassium ions to magnesium ions and CR ions. So the result shows that our membrane have a very separation properties. So it also shows the excellent repeatability and the long-time stable of our membrane for separating the normal and natural value metal ions. So for this part, the conclusion is the weakening repassive hydrogen force and the increase of pi abstraction between geo nanosheets contribute to the high stability of geomembrane in the aqueous solution. The second is the the graphene-based membranes by constructing uniform two-dimensional nanocharts with effect channel heights of 0.8 nanometers for effectively severing in the metal ions has been developed. So this two parts is my presentation. Thank you, everybody. Any question, we're welcome.
Thank you, Prof. Liu, for the wonderful talk. And we have several questions from the audience. Due to the time constraints, we may ask one or two questions. The first one is from Crystal Liang. Thanks, Prof. Liu. I want to ask why only Callium is responsive.
Oh, that's, can you hear me, Crystal Levin? Yeah, this is a good question. It shows that the chronometer have a selectivity to the ions because of the ions can captured by the chronometer because of the size and the hydrogen energy. So we can find the potassium ions is mixture to the chronometer size. So only potassium ions is responsive. So
okay.
the size.
Oh, okay. Hope this question can this answer can answer their question. And another question from Jia Mengmeng. Thank you, Prof. Liu, for your wonderful talk. How to control grafting reaction in pore?
Sorry. Which one? I didn't see the questions.
How to control grafting reaction in pore?
Oh, so we can using the plasma polymerization method, so we can control the time and the power of the plasma technology. So we just control the time. So if we want to large graphing reach, we can turn on the increase the plasma treatment time. Do you understand? Yes?
Yeah. Okay. And we have time for the last question. It's also from Crystal Liang. For PRGO, is the water be cross-linked in partially reduced GO?
Actually, the water can form the hydrogen bonding with the PRGO. It is, but it's smaller than the normal GO. So it's just a little decreased with the water, but not completely not form with water molecular. So just they still have some interaction relationship between the PRGO and water molecular, but it is smaller than the normal one.
Okay. Thank you again, Prof. Liu.
Yes.
So I give my mic to you.
Okay, that's great.
My talk.
So, hello everyone. So it's my honor to introduce the sponsor here. Sorry, I should thank. Oh, hello.
Hello.
Yes. So Si Pinsun is from Nanjing Tech University of China. So he is my good friend for many years. Okay, we meet each other long times ago. So Si Pinsun give the talk on the nanofiltration membranes from the world host ghost strategy. So let's welcome Si Pinsun.
Okay. Thank you, Prof. Liu, for your kind introduction. So I will start my talk to show the recent progress in my book on the formation of nanofiltration membranes from host gas strategy. So the focus of my research is on the development of nanofiltration membranes for precise construction, large-scale fabrication, and applications. We develop novel materials such as supermolecule and nanocapsule, and some advanced methods. And we fabricate flat sheet membrane, nanofiber membrane, and hollow
Sorry,
fiber.
Professor Xuan, sorry for interrupting. Your text is very small. Your slide looks very, very small. We cannot read. Sorry. Can you enlarge it a bit? Okay, looks better, yeah. Can you, okay, much better. Can you,
Oh,
if you can show your slide now, if you can show it now.
Okay. It's okay?
Looks much better, yes, thank you.
How about this time?
It became smaller, much smaller, very small. We cannot read. This is better, yeah.
Okay. So in this talk, I will mainly talk about the two directions in my book. The first one is how we tackle the trade-off effect by developing a host gas enhanced interfacial polymerization to precisely construct the sub-nanometer pores. And then, if time allows, I will talk a little bit on another development inspired by the host gas chemistry. Is we developed a nano capsule technology to encapsulate the modifiers of the membranes, and we can regulate the pores and charge in one step, so that our target is for the large scale fabrication of high precision NF membranes for resource utilization. And we all know in the traditional NF membranes, the reaction is very fast. It takes place in several seconds, and it's because the diffusivity is very high, so that we cannot control the process very precisely, and we cannot have uniform pore size of the NF membranes. So our question is that, can we reduce the diffusivity, and in this way we improve the controllability of the interfacial polymerization? So we look into the supramolecules, and we are mostly interested in the cucurbiturial. So we are very familiar with cyclodextrin because many of us study the cyclodextrin in membranes. And why do we want to study CB? Because these two all have hydrophobic cavities and host gas effects. And because CB has a symmetric structure, it has a better complex capability than CD. However, CB suffers from very poor solubility in water. That's why it was not interested by the membrane gas to prepare membranes. And before our study, we found only one paper in the literature. They use complicated processes and time consuming processes to modify CB to be soluble in water, and they can make a membrane in small scale, but it's quite difficult to scale up these membranes. So our question is, can we make CB-based membranes from interfacial polymerization? Because this is the most mature process in making nanofiltration membranes. So we developed a method by ion dipole effects from the protonated amines, so that we can let the amines enter the cavity of the CB. And because of the hydrophobic and the electrostatic forces, so the amines will rearrange the rotaxanes formed by the CB and the amine host gas. In this way, we can let the amine to enter the cavity, and also this host gas is formed. The solubility of the CB is enhanced significantly. The molecule is the CB molecule is soluble in this way, then we can perform interfacial polymerization. And because the volume of the amines is enlarged by forming this host gas, so its diffusivity is significantly reduced to 85 times. So in this way, we reduce the diffusivity and we can control the interfacial polymerization. We have tried several kinds of gas monomers, PIP, Parman, and DETA, and we found that long and flexible molecules such as DETA is advantageous for the protonation, which we does not need iodine acid or some other sources, so that we can already form the host and the guest. This is what we study, the solubility effect. And then we also study the performance of different kind of host guest. We found from PIP CB host guest, we can control the pore size by changing the CB concentration. And also we can control the charge of the membrane surface, because the CB cavity can cover a part of the positive charge of the PIP, so that we can let the membrane charge change from negative charge to positive charge by changing the CB concentration. So in this way, we have larger pore size and the negative surface charge. We can enhance the rejection of sulfate ions and let chloride ions to pass through, so that we can have much higher water flux and very high salt rejections, salt selectivity. Also, we tested the Parman CB host gas, because Parman is a large molecule. Its diffusivity is already lower than the PIP, so it can give us a much lower surface roughness, and also it brings hydrophilicity on the membrane surface. In this way, the membrane has very good anti-fouling performance. The most interesting one is we use DETA as a gas, because we does need acid to form host and the gas. In this way, we can make very dense surface of the interfacial polymerization membranes. And also we can pattern the membrane surface by changing the CB concentration. This we call it a self-restriction effect. So in this way, the membrane surface pattern can be linearly regulated by the CB molecules. And we use this membrane for rejection of IPA from water. We know normally this application is normally done by preparation, but we use a very tight nanofiltration membranes. We can achieve small molecule rejection, which is maybe significant for pre-concentration of bioethanols. inspired by this host gas chemistry, and we think, can we synthesize a nanocapsule and we track the modifier for surface modifiers, for surface charge modifiers inside this nanocapsule, and we put into the dope solution. So the modifier does not react with the dope solutions during the dope solution preparation step, but we release this kind of modifiers during the phase inversion process, so that we can perform the phase inversion and the surface modification in one step. We chose polyethylene and bulk, which are all classical modifiers in the literature. And we found that we can control the membrane surface charge by changing the disintegration time. We can change the membranes from negative charge to positive charge. And the surface hydrophilicity and process can also be tuned. This membrane has very good results for separation of positively charged ions, multivalent and monovalent ions. And we apply this one in rejection of various amino acids, which is also a small molecular sized organics. So in this way, we can reduce the complicated processes for interfacial polymerization and change it to a one-step fabrication of nanofiltration membranes. We have built the pilot scale production line, and we have made several kinds of modules for material separation and for water purification. And we have put our membranes in some small operations for various applications, such as pharmaceutical purification and landfill leachate treatment. So due to the time constraint, I just conclude here. Molecular encapsulation technologies based on supramolecules and nanocapsules can enhance the controllability of the IP process, and we can regulate the membrane structure and improve membrane performance in this way. And we are now working on the dynamics and functionalization of this molecular encapsulation technology, and we hope to understand deeply of the structure efficiency relationship of this technology and expand it to more application fields. Finally, we have found this new journal called Advanced Membranes. It has very high aims, and we are going to publish the first issue in very soon. We hope our friends and colleagues can submit your high impact papers in this journal. And thank you very much. I hope to answer your questions and hope to build collaborations with you. Thank you.
Okay, let's thank you, Professor Sun. So there is questions. Can you read it on the chat window?
Okay, okay.
Crystal asked Professor Sun the question about the rejections of them. Magnesium is stable, but the ions such as sodium and lithium is decreased. Why it's happened?
The rejection of the magnesium sulfate is stable, and the mono. So this one is now the x-axis is not time. Let's see. The disintegration time means the disintegration of the nanocapsule during the membrane preparation. It's not the time during operation. So hope I can answer your question.
Oh, is there any questions? So, okay, if you have question, you can. So there is.
I think my slot is here.
Yeah. So Yasun has a question. So please describe the in depth in gesture on auto-filling of membranes models configurations. Some questions about the auto-filling of the membranes. So I can.
That one is spiral one. It's a flat sheet membrane, row-to-row production, and we made it to spiral one.
So, okay, so we still have times?
No, I think we should. I think my slot is here.
Yes.
I should finish in 13:40.
15 or 40?
40. I think we should start the next session.
Yes, okay. So if anyone have the, so the Yasun has the following questions on about the UF. Is UF memory or NF memory?
NF is NF membrane.
Okay. So we should stop at this sections. So let's thank Professor Shun. So next talk is from Xiangjun Liao from Nankai University. Xiangjun will give us the topic on the effect of different surface and properties on the, sorry, okay, its properties on the outweighting behaviors of an osmophobic membranes in membranes distillation. So that's please, Xiangjun.
Okay, thank you, Professor Liu, and thanks for your introduction. And in fact, I'm in another section, but I missed the link, so I was invited to join this meeting. Today, the presentation of my topic is effects of different surfactant properties on anti-wetting behaviors of an omniphobic membrane in membrane distillation. Membrane distillation is a membrane process driven by the vapor pressure across a hydrophobic membrane. During this process, MD separate cold stream from the hot feed solution by allowing only volatile compounds to pass through it and rejecting the non-volatile compounds on the feed. For the MD membranes, separation membrane is very important to obtain the excellent MD separation membranes. We usually consider many characteristics. For example, it needs to maintain hydrophobicity, feasible pore size, reliable stability, and long-term surface life. Surfactant-induced membrane wetting is threatened membrane operation. Surfactant can absorb on the membrane surface through hydrophobic interaction, thereby changing the property of the membrane surface and pores. At the same time, the surfactant can reduce the surface tension of the feed, make the LEP liquid entry pressure decrease. In this way, the transmembrane pressure difference exceeds the LEP, which eventually lead to membrane wetting and MD failure. Well, it should be pointed out that unlike ethanol-induced membrane wetting, surfactant-induced membrane wetting is progressive. In the past decade, bio-inspired superliquid repellent membranes for membrane distillation played an important role in MD. Our group reviewed the mechanisms, fabrication, and applications of a superhydrophobic, omniphobic, and underwater superolefophobic membrane for MD. Numerous studies have shown that the omniphobic membrane have a better comprehensive performance in terms of anti-wetting, anti-fouling, and anti-scalding. In the studies, the anti-wetting properties of omniphobic membrane usually evaluated by adding SDS to the feed solution, but real wastewater may contain different surfactants. So surfactant such as SDS is not sufficient. And also different types of surfactants may cause different membrane wetting behaviors. Well, surfactants can be simply understood as a surface active agent. Usually a small amount of surfactant can change the interface properties immediately. Surfactants has hydrophilic heads and hydrophobic tails. It can be divided into non-ionic, anionic, and cationic, and amphoteric types. Each RB value indicates the hydrophilicity and hydrophobicity of the surfactant. The higher the HBLB value, the stronger the hydrophobicity of the surfactant. CMC refer to the lowest concentration of surfactant molecules to form materials. So what kind of membrane wetting behaviors can be induced by different surfactants, and how do the properties of the surfactant affect the membrane wetting processes? To address this issue, we first fabricate an omniphobic membrane. As you can see from this slide, the preparation process of the omniphobic membrane includes electrospun PVDF nanophobic membrane, dopamine activation, nano-civil particle deposition, and final fluoridation. After these 4 steps, the hydrophobic membrane are changed to omniphobic membrane. The membrane test used the DCMD configuration. The relevant parameters are listed here. The preparation of the feeds are obtained by adding different surfactants to the sodium chloride burn with a mass ratio of 3.5%. This same figure shows the membrane surface morphology. As we can see, the original membrane is composed of nanofibers with different orientations, and after the dopamine modification, polydopamine particles can be observed on the nanofibers. A large number of civil nanoparticles appear on the PVDF civil membranes. The fluorination treatment did not change the membrane surface morphology. Correspondingly, the surface chemical composition of the original were analyzed by HTS as shown in the figure. Compared to the original PVDF membrane, additional nitrogen and oxygen peaks appear on the dopamine activated membrane, and the silver peaks appear on the silver deposited membrane, and the enhanced fluorine peak indicates the successful graphating. These results prove that we have successfully modified the membrane. Well, this figure shows the anti-wetting properties of the membrane. The omniphobic membrane has a water contact angle of over 150 degrees, even for all surfactants and minerals. From these photos, none of the tested liquids can wet the omniphobic membrane. The slip angle of the omniphobic membrane is also very low. The anti-wetting properties of the omniphobic membrane is attributed to the reentrant structure with low surface energy, which makes the droplets exist in a Caspexter state and avoid the penetration of the low surface tension droplets. And as shown in Figure D, all membranes show the negative charge in the pH range from 3 to 10. And there's the omniphobic membrane maintains robustness even after the chemical and physical damage. Well, the MD performance of the membrane was first tested using a sodium chloride feed solution. All membranes remain stable during the test time while maintaining different membrane fluxes. The same EDS measurement shows that there are obvious crystals on the original PVDF membrane, while a few crystal size appeared on the PVDF-C membrane, and no crystals were found on the PVDF-F membrane. This indicates that the good anti-scaling performance of the omniphobic membrane. This table lists the 4 different types of surfactants. two anionic surfactants and two cationic surfactants. The basic parameters of the surfactants, especially the HRB and the CMC, are displayed. As we can see, SDS and SLS has a very different HRB value, while the but with a similar theoretical CMCs. In contrast, the DTAB and the CTAB have a similar HRB, but the theoretical CMC is quite different. This figure comprehensively shows the MD performance of the membranes to 4 different surfactants liquids. For SLS, the original PVDF membrane is wetted immediately after 0.2 millimoles SLS is added, while the commercial membrane and the omniphobic membrane remains stable, even if SLS accumulated to 0.3 millimoles. For SDS, the original and the commercial membrane was wet quickly, and the normalized flux of the omniphobic membrane slowly decreased. Obviously, there are two surfactants have different wetting behaviors. And for DTAB, the flux of the original membrane decreased in the later stage of the MD operation, while the commercial membrane and the omniphobic membrane also remains stable. And for CTAB, all membranes were immediately wetted. According to their results, we can see that the omniphobic membrane has a better wetting resistance to compared to the original membrane. And SDS and the CTAB has a stronger wetting ability. So what are the mechanisms of this phenomenon? First of all, I want to explain the difference between the anti-wetting behaviors of hydrophobic membrane and the omniphobic membrane. As shown in Figure A, as we can see, the feed liquid can invade the hydrophobic membrane pores to form a stagnation zone, thereby causing membrane wetting by convection and diffusion. In comparison, the omniphobic membrane makes the liquid display Caspexter state on the membrane surface, thereby reducing the liquid solid kinetic area. In addition, according to the Young-Laplace equation, the LET of the omniphobic membrane was enhanced by endowing the membrane with higher water contact angle and smaller maximum pore size. All their figures contributed to the better anti-wetting behaviors of the omniphobic membrane. Well, the various wetting characteristics of omniphobic membrane in the presence of SLS and SDS can be attributed to the different HRB values. According to the surfactants-induced membrane model, the adsorption of surfactants on the membrane makes it exist in two forms, namely adsorption states and phase states, as shown in Figure C and Figure D. Compared to SLS, the SDS with a higher HRB value tend to stay in the feeder solution and reduce the surface tension of the feeder solution, thereby accelerating membrane wetting. The obvious different membrane wetting behaviors when treating DTAB and CTAB containing solution can be explained by their different theoretical CMC values, as shown in Figure E and F. When the experimental dosage is above its theoretical CMC value, the excessive surfactant molecules from micelles and instantly adsorbed onto the membrane pore walls, promoting both convection and diffusion towards the permeate side and accelerating membrane wetting. We also use oily wastewater to verify the performance of the membrane, as shown in Figure A. Compared to the original and commercial membrane, the omniphobic membrane exhibits stable permeation flux and salt rejection rate. After the test, the water contact angle of the omniphobic membrane can still be maintained at above 150 degrees. This demonstrates that the oil folding performance of the omniphobic membrane is also good. And finally, we obtained 4 research conclusions based on this research. First, the fluorinated silver nanoparticles coated membrane possessed robust omniphobicity. The second, surfactants with higher HRB reduce the surface tension and easily wet membrane. And third, surfactants with lower CMC tend to form micelles and rapidly wet the membrane. And also omnifabric membrane perform the best when treating all in water emulsions. Finally, I want to thank my supervisor, Professor Liao Yuan and Abdul Ghani Rizab. And I also want to thank the financial support from the National Natural Science Foundation of China, Ministry of Science and Technology, and the Tianjin Municipal People's Government. That's all for my presentation. Thank you.
Thank Liao Xiangju's talk. We just have. Sorry. So we can have one questions.
Okay.
So is there any question? So I have one question, Xiangjun. What about the rejection of your memory? So you just use the one ions or just the mixture of the ion solution?
Well, we first use the sodium chloride with a measure ratio of 3.5%, and after that we use the mixture solutions by adding different surfactants into this the sodium chloride solution, and finally we use the salty solution to test the membrane.
Oh, okay, that's great. So let's the following time let's invite Professor Sipingsun to give our the introduction of other presentations. Okay, Siping.
Okay, thank you, Prof. Liu. So our last speaker is Si Yang Bing, and the talk is fabrication of carbon nanotubes, embedded polystyrene, polyacrylonitrile oil sorbent using electrospinning. And the talk is recorded in a video in advance. So we will show the video first. And Si Yang is also presented here. So if you have questions, you can type the questions in the chat box. Okay.
Hello everyone. My name is Xiang Bian. I'm doing a master and PhD combined course at Busan National University, South Korea. Thank you for providing me a chance to present my research in here. Today, I'm gonna giving a talk on fabrication of carbon nanotubes, embedded polystyrene, polyacrylonitrile combined oil solvent using electrospinning. My presentation today will cover the following content. As you can see this picture, ship accidents cause high amount of oil spill, as well as it gives the severe toxic effect to marine environment, organism, and eventually to the human. According to recent report, case of oil spill accident has been increased. The most spilled oil in the ocean are heavy oil and diesel oil, leakage of industrial oily wastewater, and oil spill into the ocean often cause contamination on the marine environment. Therefore, the importance of treatment of spilled oil has recently become more and more necessary. Spilled oil has been removed by using booms, skimmers, chemical dispersion, in situ burning, and sorption method. Of them, oil sorption using polymer absorbent is by far the most promising technique due to its high removal efficiency, good oil water selectivity, and cost effectiveness. However, conventional polypropylene solvent has still low oil sorption capacity and insufficient to use in a sustainable manner. Therefore, in this study, Polystyrene was selected as an alternative of PP due to its hydrophobic, oleophilic, and remarkable oil sorption capable among other polymeric materials. As you can see the bottom graph, PS solvent has a higher oil sorption capacity than PP, which is about 6 times. However, PS has some limitations, easily dissolved in gasoline and low mechanical strength. On the other hand, polyacrylonitrile has high mechanical strength and electrical conductivity as well as durability to the gasoline. Also, multi-wall carbon nanotube has been shown a remarkable oil sorption capacity due to high porosity and surface area. Therefore, in this study, PS-PEN CNT combined nanofibrous solvent was fabricated using an electrospinning technique to have a high durability, reusability, and oil sorption capacity. Oil sorption capacity, oil removal efficiency, and desorption reusability were evaluated using 3 different types of oils. Solvent was fabricated using PS, PET, and MWCNT. Oil sorption test was conducted with diesel oil and motor oil, which are oils sprayed at high amount in the marine. Oil have different viscosity. Motor oil is 0.3, but diesel oil is 0.001 Pascal second. As I already mentioned before, polar material like PS is easily dissolved in gasoline, so durability was tested with gasoline. Then to find optimal solvent which has high sustainability and mechanical strength, the part weight ratio of PS-PEN mixes from 10 to 0 to 5 to 5. After finding the optimal PS-PEN solution, 4 different concentrations of CNT added to the PS-PEN solution. Electrospinning is a simple and versatile fabrication method, allowing a superior control over the structure of resultant membrane with high porosity and hydrophobicity in a short time. We fabricated the solvent based on the optimized operating condition for electrospinning, working distance, voltage, flow rate, and needle size. A sorption test was investigated using motor oil and diesel oil for 1 hour. After sorption, desorption test was conducted using physical compression. Also, reusability was carried out by repeating sorption-desorption tests. Sorption kinetic test can provide a equilibrium time, sorption rate, and possible mechanism controlling this reaction. 2 different models were considered to pseudo first order and second order model. The oil removal efficiency of oil-water mixture was investigated using UVVs before and after oil sorption tests. Then result and discussion. Firstly, PS-PEN solvents were fabricated using electrospinning methods at different PS-PEN ratio. From the same image, it was found that fabricated solvent has nanofibrous structure without any spherical bead structure. This table shows some characteristics of PS-PEN solvent. PS-PEN solvent has high porosity, more than 97%, and water contact angle was slightly increased with pen addition to PS. Below figure show the durability test using the gasoline. PS was easily dissolved in the gasoline, but at high ratio of pen in PS pen presented a stronger durability, as well as from 7 to 3 of PS pen, they was not dissolved in the gasoline. Therefore, in this study, 6 to 4 of PS pen was selected to optimal condition due to the highest porosity and contact angle in the range where the solvent is well maintained in the gasoline. PSPan CNT solvent was fabricated by mixing CNT of 0.25, 0.5, 0.75, and 1 weight% to PSPan 624. The addition of CNT 0.25 weight% shows a high porosity and contact angle than 624 of PSPan. However, further increase of CNT resulted in low porosity and contact angle and thicker fiber diameter due to insufficient dispersion in the PSPan solution. Therefore, the highest oil sorption capacity was effected with 6 to 4, 0.25 weight% of PSPan CNT. Oil sorption capacity test was conducted using 10 to 0 and 6 to 4 of PSPan and different CNT concentration embedded PSPan CNT solvent. As effective, oil sorption capacity of motor oil was higher than diesel oil because high viscosity of oil can be absorbed well. Results showed that 6 to 4, 0.25 weight% of PSPan CNT has the highest oil sorption capacity. It was around 250 gram per gram for motor oil and 80 gram per gram for diesel oil. Especially, motor oil sorption of PSPan CNT solvent was about 1.5 times higher than PS solvent. This is a result of sorption kinetic test. All solvent quickly absorbent oil within 10 minutes due to capillary force of surface. After that, rate of oil sorption by solvent was slowly increased and oil was absorbed in void and surface of the absorbent due to van der Waals force between molecules. Oil solvent reaches a static state after 40 minutes in motor oil and after 30 minutes in diesel oil. R-squared value of pseudo second order model is close to 0.929 and is higher than pseudo first order model. This indicates that chemisorption is predominant for this sorption, so it can selectively absorb the oil. Fabricated solvents can be floated on surface water for a long time because they have hydrophobicity and oleophilic and it absorbs only oil. These characteristics was confirmed by contact angle to water and oil and sorption test of oil in the water. Like a photograph, all solvents have higher contact angle than 125 degrees with water, while contact angle of oil is 0 degrees. Therefore, all solvents selectively absorb oil by floating on surface of water for a long time. After sorption, remaining oil in water was investigated as well as oil removal efficiency was calculated like the graph. Oil solvent shows more than 80% of oil removal efficiency. It is result of this option reusability test. 10 to 0 of PSPan is hazardly usable because it has low mechanical strength. On the other hand, 6 to 4 and 6 to 4 0.25 weight% have strong brake strength because PAN and CNT have high mechanical strength. Therefore, they were expected to be highly usability. And like figure 12, A is surface of PS solvent after sorption, and B is surface of solvent after desorption using physical compression. After desorption, fiber structure was broken, so reusability was investigated using 6 to 4 and 604 0.25% of PSPN scientists. Reusability was measured using diesel oil and gasoline because physical dissolution of motor oil with have high viscosity was impossible. Sorption dissolution of solvent was possible up to 7 cycles for diesel oil and 2 cycles for gasoline. In addition, 6 to 4 OPS pen shows oil removal efficiency from 78 to 58%, while 6 to 4 0.25% of PS pen CNT present oil removal efficiency from 71 to 79% during 7 cycles without any damage of solvent. Therefore, 6 to 4 0.25% of PS pen CNT could reuse them with higher oil removal efficiency. I would like to conclude our findings. Firstly, in order to make up for limitation of PS solvent, PS pen CNT solvent was fabricated using electrospinning. Reusability and durability of solvent increased by mixing pen, and also oil sorption capacity and reusability of solvent was enhanced further by adding CNTs. Though experiment, optical condition of PS pen CNT solvent was founding based on the high oil sorption capacity, reusability, and durability in gasoline. Therefore, we expect that this PS pen CNT can be used as a sustainable solvent for oil cleaning when the ship accident and oil spill is occurred in the ocean. These are references for this study. Thank you for your listening. This study was financially supported by Korean government.
Thank you, Xiang. Thank you for your talk. Are there questions from the audience? I have one question for you. Are there any commercial solvents for this application? And how's your performance compared with commercial solvents?
Conventional solvent is my solvent oil sorption capacity is 248, but conventional solvent is 19. So I think my solvent is higher than 20 times, 10 times.
Okay. Thank you very much. Due to the time restraints, we do not have more questions. And thank you again, Xiang. And thanks for all the speakers, the 4 speakers in this session, and all the audience for this session. And I see Prof. Shang from Australia also attended this session. The organizer asked me to announce one message, that the closing ceremony is already start at 4:14 p.m. So the audience, please move to the room for the closing ceremony. Thank you very much, and have a good day. Thank you, everyone. Thanks, Prof. Liu. Okay. We meet again here.
Okay, thank you, everyone.
Thank you.
Okay, bye.
Bye bye, everyone. Bye bye, Liao Xiangjun. Okay.
Bye bye, Professor.